The various methods I'm going to show you, in particular the first method 1 and method 2 of solving nonlinear equations, are really just particular ways of solving a pair of equations, at least one of which have some nonlinearity to them. So let's start with the graphical method, and my circuit is on the right hand side, and I'm showing you the same voltage source resistor, the Thevenin pattern in connected to the device D. And below that, I have the equation ID equals AE raised to BVD, which is the device equation. So as before, let me go ahead and do all the first few steps. I go ahead and write the node equation at VD, and I got that. I go ahead and substitute as I always do in the node method for the current using the device relation. And just for fun here, let me keep that separate for now. In the analytical method, notice that you ended up with these two equations, and you had to solve for these two unknowns, and we did that using analytical methods. In this video, I'm going to solve these using the graphical method. In order to do so, here's what I'm going to do. I'm going to start by rearranging the terms in my equation 1 to make it a little bit more convenient to draw the graph. So notice in equation 2, I have ID equals something, and then I have an expression in VD and ID. So what I'd like to do is let me start by taking this equation here and expressing it in a more of a standard form so I can get something symmetric to equation 2. So let me express this by pulling ID to the left-hand side all by itself, and so I get something like this. Okay, so I get ID on the left-hand side, and then I'm going to move VD minus V divided by R to the right-hand side. So let's start with minus V divided by R, and when I move that to the right-hand side, it becomes V divided by R. And then when I move VD over R to the right-hand side, I guess minus VD over R. And I've simply not done much here. I just have done some rearranging of the terms in equation 1. And since I haven't done anything unique and different, I'm just going to label this as 1 prime. So I just got this from equation 1, and I'll just label that as 1 prime. So continuing with the method, and now I'm summarizing for you equations 1 prime and 2. We want both of them for ID on the left-hand side expressed as a function of VD. And in equation 2, it is nonlinear. So the graphical method can be summarized as follows. To start, I want you to notice something. Essentially, all we're trying to do is find a solution, find a value for VD and ID that satisfies both equations 1 prime and 2. That's all we're trying to do. It's just math here. There's no circuits here. We're just doing some relatively simple math. Okay, we just have to figure out what ID and VD are, and we'll use the graphical method. So to do the graphical method, what I'm going to do is I'm going to plot the two equations in a pair of graphs. Let me first start by plotting equation 2. And in equation 2, I'm going to plot ID equals A raised to AE B VD. I'm going to plot ID equals A times E raised to B VD. Okay, that's my equation 2. And this is the plot that I get for it. Okay, it's a plot that I had before. And so that's my equation 2. Notice that this plot here is simply the constraint on ID and VD imposed by the device. I have this little circuit here containing the Thevenin equivalent and connected to the device. Equation 2 is simply the constraint imposed by the device. Okay, the device properties are such that it is going to constrain ID and VD into some relationship. This constraint that I plotted here as equation 2 is simply the constraint imposed by this device. Okay, next, let me go to 1 prime. And in 1 prime, let me go ahead and plot the 1 prime equation. And that equation, rewrite that here, is V divided by R minus VD divided by R. So I'm just going to plot that equation for you in a second graph. So how do I plot this? So notice here, when VD is 0, then ID is V divided by R. So that is 1 point on the straight line. Okay, notice that this is an equation for a straight line. It's a linear relationship between ID and VD. Next, when ID is 0, so when ID is 0, then notice that R and R can be cancelled out, and V will be equal to VD. Okay, so when ID is 0, V and VD are equal, so therefore VD equals V. Okay, so this is the line when ID is 0, and for that, VD equals V. So then I get this straight line for the relationship between VD and ID according to 1 prime. So what's the slope of this line here? Okay, can you tell me what the slope of this line is? Let me give you a few seconds to think about it. Okay, from the equation 1 prime, from this equation, the slope is simply given by the coefficient of VD, since the slope is negative, which is why the line is inclined the following way. So the slope here is simply minus 1 divided by R. So that is my constraint that relates VD to ID. And where did that constraint come from? That constraint is the constraint on ID and VD that has been imposed by the rest of the circuit. So if the first constraint was imposed by the device, then the second constraint is imposed by the Thevenin equivalent that is connected to the device. Okay, the Thevenin equivalent was the V and R in series, and those two impose a Thevenin constraint on the terminal pair that relates to VD and ID. So now my next step is given these two graphs for ID versus VD, and clearly those are my two constraints. The graph 2 says that ID and VD must be somewhere on this trajectory. Graph 1 prime says, well, I'm not going to let VD and ID be anywhere else but on this curve. Okay, that's it. Both of them are fighting against each other and telling each other, nope, I'm not going to allow you to do anything. You have to be on my curve. So in this case, I have two curves, and I need a point that satisfies both curves. And that is easy enough to do. And I simply have to go and satisfy both these constraints, and that will give me the answer for VD versus ID. Before I do that, so I can go and solve it for you, let me go and pick some values for the various parameters. So as before, I'm going to pick V equals 1 volt, R equals 1 ohm, a quarter of an amp, and B to be 1 volt inverse. Okay, so I'll pick the same parameters as I had done in the when I did the analytical method. Next, what I'll do is I'll substitute these parameters into the two equations 1 prime and 2 and rewrite them with the parameters substituted. So for 1 prime, I get ID. Since V is 1 and R is 1, I get V divided by R equals 1. And then since R is 1, I get minus VD. So this is 1 prime once I've substituted the values. And then for equation 2, what do I get? I get ID equals AE raised to BVD. A is 1 quarter, so I write that down. B is 1, and so I get VD up here. So I have my two equations in terms of the parameters I've chosen, and now I can go ahead and plot the two equations and see where they intersect. I've given you the form of the graph here, and so let me go ahead and plot this. Let me go ahead and plot 2 first. 2 looks like this, where this point is 1/4. That was the A point. This curve, as I said before, this curve is simply my equation 2. Then let me go ahead and plot equation 1 prime, and as you recall, that looked something like this, where the VD intercept was V and the Y-intercept was given by V divided by R, and in this case it was 1 and V was also 1. So those are my two curves, and here's the intercept. Here's the point where the two coincide. And then I just have to go and find the values of ID and VD where they do intersect. So this point there will be 0.56 volts, and this point will be 0.44 amps. Okay, it's the same as what I calculated in the analytical method. And so let me go ahead and write that down. ID equals, in this case, 0.44 amps, and VD equals 0.56 volts. So basically, I've just taken the two graphs, superimposed them. This was 1 and 1 prime rather, and the nonlinear one was related to equation 2. So before I jump off to one other thing, to define something for you, you notice this curve here. Okay, this is a straight line that reflects the Thevenin constraint that I apply on my nonlinear device. And I mentioned earlier, we're going to do this again and again and again. I think you will see this at least 10 more times in this course, where I take a Thevenin equivalent of the following form, some voltage V, some R, and apply that in series across something interesting. And so this line that I see here is the constraint imposed by the Thevenin equivalent, and you can see that from equation 1 prime. Now, so there's a name for this line. So this line is called the load line. Okay, you will see more reasons for this later, but this line is called the load line. Let me show you one other little trick, just in case you didn't completely get how I solved the graphical method. But one little trick here, if you like PowerPoint, you will enjoy this, and if you don't like PowerPoint, you will hate me for it. So if you look at these curves, I have my two equations in ID, the 1 prime and 2, and I've plotted them for you here. Okay, on the left-hand side, I plotted equation 2, right-hand side, I plotted equation 1. And fundamentally, all that the graphical method is doing is simply superimposing the two graphs, and by superimposing the two graphs, it is finding the point where the two curves intersect. Okay, and this is what you get. Okay, so let me do that again. So I take one of the curves and superimpose it on top of the other curve, given the same axes and the same scales for the axis, and then I go ahead and find the solution for the point where the two intersect.